All right, so we're back here. So let's work on a few problems to apply what we just learned in the last one. So we'll start with 9.1, 9.10, I guess, I should say, on page 405 in the 4th edition. So this problem is asking us, a person who claims to be a psychic says he predicts the outcome of a flip of a fair coin more often right than wrong. If we want to test this claim, we could use the data from an experiment in which he predicts the outcome for n flips of the coin. State the parameter of interest. So what is the parameter? The parameter of interest and the hypotheses for significance test testing the claim where the alternative hypothesis, so the alternative equals the psychic claim. So basically what this is asking us to do is what exactly are we trying to figure out, right? So how would we, what's going on in this? So the parameter that we're interested in, so the parameter is a proportion, and this proportion is correct predictions. So what is the proportion that this person is correct all the time, right? So since it's a coin flip and we know that in the long run, long expectation, that the coin flipping is going to be 50-50, so we would say that the null hypothesis is that, in the long run, that the psychic will predict, so P is going to be equal to 0.5. So that this, that's the null, right? So that this person could guess it like half the time. So another way to think about this, right, is, so what's like the alternative then? So we would say then that the alternative hypothesis, and so the psychic is claiming that he's better than half, is that we would say P is greater than 0.5. So his proportion of giving correct answers is greater than half the time. So that's what that's how we would break that answer down. All right, so fairly simple. So let's look at 9.15. 9.15. And this is about dogs and cancer. So studies looking at dogs to be trained to detect if someone has lung or breast cancer by smelling breath. The researcher trained 5 ordinary household dogs. So we have 5 pooches. And found treated by scent alone exhaled breath samples of 55 lung cancer patients, and 31 breast cancer patients. And there are, what do they say, 83 controls, so people who do not have like cancer. So they give it a correct. If he sits in front of someone that has it, once trained, the dog's ability to distinguish cancer patients from controls was tested using breath samples from subjects not previously encountered by the dogs. So it was blind. So P, so we're looking at a proportion, right, is the probability of a correct cancer sample. So, see, there are 5 dogs. Set the null hypothesis that the dog's predictions correspond to random guessing. So, the way that this is set up is that, what is the way this is set up? Placed among 5 samples when the other 4 are controls. So basically it's saying that the way that this experiment is set up, right, is that there's 1 person, 2 people, someone with cancer, another person without cancer, and this one does not have cancer. So the dog in this experiment, or what they're trying to do is, so there's a little dog is right here, and we have little ears. Dog is trying to figure out who has cancer, right? So this is the way this is set up. So question A is asking us then, given that this is the setup, what is the null hypothesis that the dog's predictions correspond to random guessing? So if it's random, so that means that there's like a chance that anything could be right, or that he could like guess it. So the null would be there is a one person out of the five, so they would eventually just find the person who is right. Would be that the proportion correct is 1 out of 5. So, part B is asking us, set up the alternative hypothesis to test whether the probability of a correct selection differs from random guessing. And so this one is pretty simple. So we would say first, the alternative hypothesis. So it doesn't have a specific value, and it doesn't say that the dog is better or worse than. It's simply saying that this is not this, right? So we would say that this is not equal to a 1 in 5 chance, right? So the dog could be worse, the dog could be better, right? In the way that this is set up. We look at part C. Set up the alternative hypothesis to test whether the probability of a correct selection is greater than with random guessing. So greater than is key. So we would say the alternative hypothesis is that the proportion of times a dog correctly guesses the cancer sample is greater than 1 in 5. So fairly straightforward. And then for part D is asking us, in one test with 83 stage 1 lung cancer samples, the dog correctly identified the cancer sample 81 times. The test statistic for the alternative hypothesis in part C was z equals 17.7. Report the p-value 3 decimal places and interpret. Basically, the way you'll recall that when we think about like p-values, right, they correspond to z-scores. So for example, the one for 1.96 is like 0.05. And I think 99% is 2.575. And I think this would come out to 0.01. I believe that is correct. And so we know that if we have a z-score of 17, point whatever, 75 or whatever the number was, right? This is really small. And like, we know there is a level for 0.01, which is like, 0.99, whatever that is. That z-score is pretty small. But this is going to be to 3 decimal places is like this. So our interpretation then is essentially 0. So we know that the probability of a correct guess based off of the dog's success is better than random guessing. So pretty dang good. Pretty dang good. And we'll do our last one, 9.22. Garlic to repel ticks. I picked this one because my mom is deadly fearful of ticks. And one time she got one in her belly button and she was terrified and screaming. It was really funny. Also reminds me of that Brad Paisley song, I'd like to check you for ticks. Or the song is just called Ticks, but there's a line, I'd like to check you for ticks. And he talks about going out in the country and with someone that he's interested in, and he checks her for ticks. And so I think the song is funny, and I picked this problem because I thought it was funny. So enjoy that, if you will, right? And if you don't know that song, well, now is the time to learn. So in this question, it's like it says, the study considered whether daily consumption of 1,200 milligrams of garlic, 1,200 mgs of garlic, could reduce tick bites. The study used a crossover design with a sample of Swedish military conscripts, so people who were enlisted in the military. Half used the placebo first and garlic second, and half the reverse. So some people got the placebo first and garlic, and then some people got garlic then placebo. The authors did not present the data, but the effect that they described is consistent with garlic being more effective with 37 subjects and placebo being more effective with 29 subjects. Does this suggest a real difference between garlic and placebo, or are the results consistent with a random variation? So, first question is, if we look at part A, is so what is the identifying the relevant variable and parameter, right? So what we're trying to figure out is, does garlic work more than a placebo? More than the placebo. And the parameter is that we're identifying is the proportion of folks where garlic is most effective. Because that's the basis of the study, that's what they're trying to figure out. If we look at B. B is asking us, stating hypotheses for a large sample two-sided test and checking that the sample size guidelines are satisfied for that test. So what do we know, right? So we know that if it's just like a 50-50, so we would say that the null is that the probability that garlic is more effective is 0.5, right? And since it's asking us for any difference, right? So it doesn't say it's positive, it doesn't say it's negative. This is the probability this does not equal 0.5. And so when we think about the sample size, this is effective because it's greater than 30, and there are more than 15 successes and failures. So pretty straightforward here. So then we wants us to look at C. C is asking us to find the test statistic value. Okay, so when we think about, so what exactly is the test proportion here, right? So the first thing we gotta do is find the proportion of effectiveness, right? So what do we have here, right? So being more effective, so we have what, 37 and 29. So we had 37 people with garlic, because this is crossed, so everyone got it, and then 29 were more effective with the placebo, which is 66 total people. So the first thing that we're going to figure out here is the proportion. And so this proportion in this sample is 37 over 66, because we're interested in the proportion where it's more effective, and this is equal to 0.561. So then we figure out the standard error, and recall that the standard error is the proportion of the null minus 1 times the complement of the proportion divided by the sample size, and we put that under a square root. And so because the null states that there's basically a 50-50 shot, so this is 0.5 times 1 minus 0.5 divided by 66, put that under a square root. And so the standard error is going to equal 0.062. And then we get the z-score, which is going to equal the estimated one minus the null hypothesis divided by the standard error. And so in this problem, we know that the observed one is 561 minus the null one here, which is going to be 0.5. divided by that standard error is 0.062. And if we solve this, the z-score is going to be 984. If we go back and look in the back of the book, we would see that this p-value is equal to 0.33. And this is not very extreme because it doesn't meet our magic threshold. And we would basically say that there is no strong evidence that garlic is more effective than a placebo. So, hopefully that seemed pretty straightforward. We'll kind of pick up similar concepts in the next video.